All right, recording, everything's there. Welcome. Losing track, sixth lecture today. I'm going to summarize a little bit what we did yesterday because at the end there were like 5 minutes or so missing. We talked about application of the formalism, second quantization, to some example in condensed matter physics, and I picked superfluidity because this is catchy. It is a fluid that flows essentially, naively speaking, without friction. So it just flows. If you let it go, it keeps going. It's like the superconductivity where the electric current flows under certain circumstances. You have to prepare this material here, for example, the helium, and cool it down to almost absolute zero for this to happen. Very unusual behavior, like water, although the water is not gonna behave like this. Macroscopically, we always have this friction, but here it's an interesting case where you don't. So the Landau argument is just an energy momentum consideration. You can think of it as, so the fluid could be think of it as a big particle of mass m, and then there's a little guy, a little droplet there, and they all travel at the velocity v. I'm not even sure if I want to include this in this m or not. This is tiny compared to this thing. This is macroscopic. This is just one little guy. So it's either little m, big M, or this is big M minus little m. But big M minus little m is the same as the big M. So you have this thing in there. And they all go at the velocity v. This contributes hardly anything to the momentum and the energy. But then you ask, oh, say this goes ahead, speeds up a little bit with respect to the rest. Maybe others kick him. There's a interaction between the particles, and it gets a kick from there, and it moves now with this wave number k thing, so it gets a little bit more momentum, and then the rest has to slow down. There's a kick back. It's very tiny because this is such a tiny excitation, but that's the idea. So can you satisfy this? Can you make one go ahead and the others slow down a little bit? Or can you not? Usually you can, right? We let's say all these particles, we walk together, we kick one, and then he goes faster, and I stay behind it. Of course it works. But not always. If the relation between momentum and energy is very special, then I give him the kick. And that says what momentum does to him and me, but maybe I need more energy than that kick provides. There isn't enough. If the energy grows faster with the momentum than what you're used to, so usually you have this thing, this is the momentum, let's say K, H bar K is the momentum, and then we have this energy. It's a little epsilon because it's just a little particle, specialization. It's still energy, and if you give it a kick, then you have to also provide this energy. But it could be the case that this just goes up fast. Then it's not enough, and that's the case in certain materials. That the dispersion relation starts very fast. So if this is, in this case, you have a superfluid behavior, and this is an ordinary fluid. It's just my two simple cases. So it's the second one, H bar squared 2m, and then sum over all the k. These are the momenta is composite because of the negative, and the k squared. It's the normal branch here, ak AK, and then we added an interaction, something that controls the strength, something that makes it look good, something that we needed to have a sum here instead of an integral, quantization in the box. So KLM, because we have 4 oscillators and 1 momentum conservation. So the sum of all these momenta, these things shouldn't change the momentum. This is basically the momentum here. So if they take momentum, stick with the number, I guess. So it was K and L. So I add momentum K and momentum L into the game. I take away momentum M. So what else do I have to add or take away? What else do I have to take away? So it fits. I take away K and L, but not N. No. I have momentum conservation in the interaction. It's this so-called hardcore interaction. If you write this in position space, then your 2-body interaction was just before this lambda half. That was at x minus y thing. You can all move freely, but when they are at the same place, then actually they kick. And so now this can be rewritten in a bunch of steps. The most important one is a Fourier transformation, which means you change your oscillators into a different set of oscillators, which are then the effective excitations, the ones that are like the real excitations in this interacting model. So this extra term messes really with what is a fundamental object in the theory. And now I don't know how this looks. It looks very nice, that's for sure. I don't know where K equals 0. I don't think K equals 0. Maybe K equals 0. I can add K equals 0 in here, right? Because my epsilon for K equals 0 is 0. B K dagger, B K dagger. These are the new oscillators, and it's just like a kinetic term here, and nothing else, because I neglected a lot of things. I neglected the higher order term. So this is plus order n 0, where n is the particle number. So there's also infinities and all this, but this is the main part. And epsilon is the dispersion relation, the one that I pictured there. Square root out of h bar squared k squared 2m all plus the interaction lambda n l squared minus lambda n l squared. That's what you find. This is a bit too precise, really, because this wasn't precise. There are n's. You can also expand this in n, because there would be other contributions in this order, but I still keep it like this. Looks nice. If the kinetic term is much, much bigger than the interaction term here, then I guess you can just neglect this, and this takes away the square, then you have only this kinetic term. So far out here, this thing doesn't matter. You can also just set lambda to 0. No interaction. Of course, you get your free particle thing. But if this kinetic term is small compared to the interaction, strong interacting, then we have to expand this properly. So expand it. That's the small guy. I'll keep this squared. I'll keep the mixed term, but I forget this squared. So then epsilon of k is square here, this one, the mixed term is 2 times h bar squared a squared m lambda n l, right? That's the mixed term. And then 2 and a or square root lambda n m l h bar k, or like k small. Really, what it is for this k small doesn't mean anything. It's a unit. It's a unit. Smaller than lambda and well. So this is the case. So then we have the linear into the one behavior down there, and it really looks like what I've drawn there. And then can't easily satisfy energy momentum conservation, because energy momentum conservation demanded a la Landau argument that this epsilon of k has to be smaller or equal to the velocity of the fluid times h bar k. Is this the case? Well, I don't know. I don't know how fast my fluid is moving, right? Can I satisfy this? Is this epsilon, is this smaller than that right-hand side? The convenient thing is that there's already an h bar k. I just have to look at what the degree factor is. Well, if the v of the fluid, I can write the left, so put the whole thing in here. So lambda n ml square root times h bar k. Is this smaller than v? Well, I don't know. It depends on v, right? Take this away, and then you see your critical velocity is just this lambda n ml. If the fluid flows be larger than what I defined as v critical, larger than that, then it's satisfied, then you will create the excitation and you will slow down the fluid and you have a breakdown of fluidity. And if the velocity is smaller than this left-hand side, it's of course not satisfied, and then you can't kick. Yes.
Why does it matter for superfluidity how the fluid interacts with itself? Like, why? I would imagine that the most important thing would be how the fluid interacts with like the other stuff that it's connected to. But we don't look at these kind of interactions.
We don't. So really, if you have a container, usually they talk about you have a container and then it flows there, and the fluid, even the superfluid, actually sticks to the side. So there's, I'm not going to call it friction. It's just sticks there, adhesion or something. It just sticks there. And if you move this surface, or if your fluid flows, whatever, you have a relative velocity, then there's no sticking together of these parts. There's no interaction between, no shear. There's no friction that then stops all the bulk fluid flow. So that's why it's kind of an interior thing than rather than the boundary. And it does stick to the boundary. And there was this, which I briefly mentioned, you have this container with the fluid in there, and you think, oh, I have my helium. The helium sits there all the time. I mean, you cool it down, and it just sits there. Really, it boils. It's like water. If I bring water to above its boiling temperature, then this thing. And here, liquid helium has a boiling like 4 Kelvin. If it's around 4 Kelvin, it looks like boiling pasta or something. And so it boils well boiled. Point is that it sits in the bottom of the container. Then you go superfluid by to whatever it was. Suddenly it's all still. There's no bubbles and nothing, and it starts to creep up here. It wants to stick to the container, to the vessel. Even if there's gravity, which used to pull this all in, it is so sticky. I'm trying to say it actually does stick to the surfaces and wants to be there so much that this is stronger than the gravitational pull. And it even goes all the way down. Well, and then it collects here, and now it collects enough, and then at some point, rips. That's the videos that you see, and you should look at them because they're not related to our computation. Really just an example, and then leading out of any window here. But from the technical point of view, it is very relevant for us and interesting, and then this other is just a nice story around it. There's a lot, an infinity of more things you can do. To go and study condensed matter physics. Really, it's very exciting. But we here, at least not now, we won't do it now. We want fundamental particles and relativity, so we're moving to relativity. So this is not the relativistic dispersion relation. Actually, how does the relativistic we had this, and then we ask. I want to write down a model where the interactions won't spoil the relativistic dispersion relation. So I start with a relativistic invariant theory, and I want to keep it that way. So what we need is a way to ensure this. Like we have to have a little formalism that builds all this stuff in. So we are going to write down lots and lots of formulas. It's very little physics today. It's a list of formulas, and you probably know most of them from other courses, but I don't want to assume this just for everybody. So I am going to review all the special relativity stuff, and then we'll see what you know. The chapter is called. So we go classical, right? It's classical relativistic field theory. Our new starting point now. This all was introduction, essentially. Realistic quantum mechanics didn't work. We need many particles. We went to many particles, and then we had this example. And now we go back to field theories with some relativistic invariance, and then we start to quantize it. So what's the point? Where is relativity coming from? Because it really comes from locality. So the principle of locality. We won't finish this entire chapter today. This was yesterday's and today's plan, so this and the Wednesday. So this is a big chunk. And we start with locality. What does that mean? I'm going to write down the interaction of two bodies according to Newton's theory of gravity. Say it's gravity. Then the equation of motion for mass 1. So they sit in positions R1 and R2. Then 1 has an acceleration at time t, which is given by gravitation constant, mass 1, mass 2, divided by their distance squared, and the direction from 1 to 2, I call E to 1. So this is E to 1. The first one is where it's pointing to. So EIJ is RI minus RJ, RI minus RJ. Just to, it's a unit vector. It points to the first one. So I have one this mass 1 to be attracted to mass 2. We're going to put the 2 in front. Really not important. I mean, this is the right direction, but we'll find it the other way around. So then M2 R2 acceleration T is equal to the same thing in the opposite direction. Newton's third law. E1, 2. This is also Newton's. Now, the point is that this theory is non-local. What does that mean? You have the t's everywhere, so everything has happening at the same time. The acceleration of mass 1 at time t. So here, say you're mass 1 and you're accelerated, and that at time t depends on the position of mass 2 at that time. So if someone else is moving the sun, I don't know, there's some sudden change, you will know instantly. That is non-local, non-locality. So this theory is non-local. And there's nothing wrong with it. In fact, you've studied this at length, at huge length, if you remember all this duration in Kepler's orbits, and it came out beautifully, right? Ellipses. It has a nice answers. It's a nice mathematical theory. There's nothing wrong with non-locality and action at a distance. It's just not observed. The speed at which the signals here propagate, so say it does move, we'll know really soon. It takes how long for us to know that the sun has moved or does something funny, switch off the light? How long does it take? Do you remember?
Like 8.
About this 8, 9. I remember 8 is probably rounded up to 9, somewhere in the middle, say 8.5 minutes. It's not nothing, right? But it's also a big distance. So it's not observed. How do we make a model that respects this locality so that we don't know immediately what's going on at a distant place? We make the interaction, it's called the force, itself a dynamical object, and let the force information propagate somehow. Something's happening, something's moving here, and then we have a disturbance in whatever, in the force field. And then this disturbance propagates like in a funny way, like a normal wave, like a wave, and then arrives anywhere else where someone else sits and receives this information. So you know Maxwell's theory, it looks like this. So Maxwell's theory of electrodynamics looks like this. So it's for the fields E of R into B of R and P. And let me just write them down for the fun of it. So divergence E of R and P is 1/epsilon 0 rho R and T. Then the curl, you don't want to copy this. I'm not going to use this for anything. I'm just going to point out something and then erase it again. This divergence B R2 is 0, and the curl of B of R step dividing down all the arguments. A R P plus 1 over C squared B R into B. So this is just the dynamics of the field and the object here down there, which is feeling this force moves according to this. Again, M R I R of T is equal to whatever its charge is, Q, say, and then the E, where we are, when we're there, what the field is at the time, plus R, I, velocity, and T, B, R, I, T, T. Okay, so what I wanted to point at, these are local equations. Derivatives at this place, time, and derivative is equal to what's happening here, local. There's no other time, there's no other space. It's all the same R. It's the same R everywhere here, and the same T. No different R or a different time. And then the acceleration, so two dots, acceleration at time t matters only what the field at this point says at this time. So super local, right? Super local is not a term, it's just local. Local. There's actually something like ultra local, but if you have a discrete space, then if it really just the neighbors, you call it ultra local. If it is a little bit further away, you call it local still. If it's not just far away, anyway, it's a local theory. So local. So that's the evolution. Go from here, the model with action at a distance to this. Doesn't have action at a distance. It just evolves, it propagates into space. This has a consequence. So I mean, we wanted the components of E and B satisfy a wave equation. I can stick them into each other. So for example, I can put what do I do? What I need? What am I doing? I apply nabla on this, then the nabla arrives here, then I use this. So I do another curl, then I have a curl of B. This curl of B, I insert this. Here's one time derivative, I get another time derivative. So I end up after some massaging with 1 over c squared, t squared minus nabla squared, on the plus. Let's do this, Laplace of some u, and the u could be any of the components, dx, dy, dz, dx, dy, dz. We have this equation, and this guy is dx squared minus plus dy squared plus dz squared. And the solutions are, you know, the waves that propagate at this speed c, which is very fast. Kilometers per second, 300,000 kilometers per second. And that's fixed. Can't even go slower. You know, it's not just a speed limit, it's also, I mean, it's both ways. It can't be faster or slower, it's just fixed. And now you remember when you heard this the first time, this is just weird. You can't have something that for everybody has the same velocity. What if the two of us have a relative speed? How can this be the same for you and me? Then doesn't it means probably that the theory only works for you or for me and not for both of us. And then they tested it and they saw no, it does. And then okay, we have to change how time and space well, it really is measured, and then everybody has its his or her personal time. So every inertial observer has their own space and time, their own lengths, their own logistics, their own clocks, and all the story. So you end up with something that's called the Lorentz transformations. So Lorentz go from coordinates. I mean, this is space and time coordinates. I really should have written space and time before that. So space in time coordinates of better of space and time coordinates between all space and all events between inertial observers, the relative speed, between the inertial observers, okay, relative velocity. Looks like this. The T, it's gamma factor, the T of the for the other observer, and then you have to do some funny business with the space, which means I'm happy with this. T is some factor times T prime. It just means that there's a different unit. Basically, one time goes faster than the other, depending on the relative speed. So this is time dilation. This factor from the times time dilation. And then we have also a dependence on x. So the time here doesn't only depend on the time there, but also where you are. It's called relativity of simultaneity. Relativität der Gleichzeitigkeit, much easier to say. And then x prime is a similar formula. It isn't that x. This is easy because you also have this in non-relativity, just the Galilean transformation. If something moves, this guy sits always at its origin, but it moves, of course, it changes its coordinate here. So this is just because it's moving, and this is the length contraction. So that's in 1D. And it has the property that a certain combination of these coordinates, x and t, has the same value as the same combination of x prime and t prime. Where's my? So it follows that this thing, c squared t squared minus x squared is actually the same as c squared t prime squared minus x prime squared. This would be a nice exercise to verify this, but I'm sure you have done this. Have you done that? How many times? That's enough. So that's what is preserved. So I'm not going to do this. If we work in 3 dimensions, I can put a little arrow on top of this. So this is now in 3D with this arrow, and this is the ordinary square. And why am I saying this? Because now now we're making starting with some formalism. We have an invariant object, so we think of space-time as something geometric, as an object, like this blackboard, and then these are just coordinates on this geometric object, and you can choose this or this. It's like you have a plane, and you put a coordinate system. One puts a coordinate system like this, and the other puts their coordinate system a little bit at an angle. I don't know why. This person is funny. And then you have different coordinates, and you have a map between them. So his x is her combination of x and y, and you get this combination. So you have it here too, but it's not like the normal Pythagoras, and you have this minus sign. So we define Minkowski space is R4, but with a funny signature, so it's R13, Minkowski space with metric With metric, G, no, eta, mu, and that looks like +1, -1, -1, -1, and 0, and 0. If you've seen on the first page of my lecture notes, there is in the upper corner in red plus, minus, minus, minus. If you wondered why, it's because I keep forgetting what metric I'm using, because all the books use different ones. So you could use minus, plus, minus, 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 or minus, plus, plus, plus. You could also say time is down there. This thing is x squared plus y squared plus z squared. And then we have the cb squared. And then, parentheses. Really like this. But you can also multiply this equation by -1. It doesn't matter how you do it. So we're going to stick with this. It's, I think, what Keskin Schröder does and what the tutorial for quantitatively uses. And still, I keep forgetting. It just adds minus signs here and there. And when you read the book, you should also first look at what metric they use, because otherwise you get confused by minus signs. So using this metric, the mu are indices that run from 0 to 3. And we put these coordinates into a so-called 4 vector, that's x mu. And because I want them to be all lengths, I have a ct here, and then I have an x and a y, and I have a z. Or if you want it shorter, I write it like this. So this really means the x0 is the ct, and the x1 is the x, and the x2 is the y, and the x3 is the z. And with all these definitions, I can write this invariant, the one that's the same for all observers, no matter how fast they move relative to each other. So the choice of your velocity is basically the choice of your coordinate system. So independent of how you choose your coordinates on space-time, you always agree on this, and that's now the norm of that guy. So x, or the norm squared, or it's squared. So this is the most dangerous notation, because I just said that x2 is the y component, but this thing is the square of this thing. Oh dear. So this is now the square. We will never worry about the second component of this thing. Why would we? Why would we care about the second component of this? We care about the first component. Yeah, I don't know. I hardly ever write x with a 2 in this sense, as the second component. If I do, I'll tell you. If you see this thing, it's the square of x, the 4 vector. And also, like you should really think of this x is the object, the 4 vector. The x mu is a component of the 4 vector. Like my teacher back then, they put a little filter underneath. I thought this is really doesn't look nice, but in three dimensions you put this arrow on top, so it's also funny there. We're not going to do this. You find this in a book. And Damen are the guys who taught me, but let's forget about it. This is just the 4 vector, and this is its square. And the definition is you sum over mu and mu from 0 to 3 x mu with this metric eta mu there, and that is chosen such that you get this combination. So this is diagonal. You only have one the same, and then the 0 0 and 0 0 is this. So you get ct all squared, 2 of them, minus, and then x vector squared. I'm going faster now. So that's the square. And now we can do lots of stuff with the square, I guess. Now, a Lorentz transformation, instead of writing these components, is now a linear transformation which leaves this square invariant, because that's the type of the combination. So we can turn this around. I don't know how you derive this. You can derive this on physical grounds and Michael-Morley experiment and do all these little things, and you get this and you find the invariant. But you can also say, okay, Minkowski space is what I have here, this metric. Now give me all linear transformations. Linear transformation can be written as a matrix that preserve the square. It's like a rotation, just in cosmos. And here starts the funny business. This mu is now downstairs. This was upstairs and now it's downstairs. And the rest of today is probably go up and downstairs. And then another thing about the summation convention. Here is the sum, but this I'll write short as x. Everybody does. You will, without summation sign, still implying the summation, and this is called the Einstein summation convention. If two indices repeat, and one of them is up and one of them is down, then you sum. You sum with this. You just sum. If two of them are up, then you go back and look where you messed up. So that usually doesn't happen. That's why I'm starting to put this down. This is another cute thing. So one should be up and one should be down. If you're up and down, they got it up, they got it down. If this happens, something's bad. So here's the sum of this. So this is really like a matrix. And now I want to find the condition on this matrix so that it is actually a Lorentz transformation, so that this preserves the square. So I go like x prime mu, beta mu is equal to plug this in lambda mu. Now we don't use mu, we use rho for here, and then I have an x rho. This is the first transformation. Then I have lambda mu sigma x sigma is the second transformation. Then I have this sticking around mu, and this should be the same as the square without the primes. So it should be x, and then picking the same indices here so that I can easily compare the two sides times eta rho sigma, and that should work for all events. So it's a condition on lambda that should be satisfied for whatever the x is, and then you conclude that all the rest is equal. So this is equal to this. Lambda mu rho, lambda mu sigma, eta mu is eta rho sigma. And this is a first equation. And there's a sum here and there. The sum you could put into matrices, and now is the part where it gets confusing for the, I guess, third time. First was that the speed is constant. If I define, this is the definition, let lambda, the object without any indices, be a matrix, and I put in the matrix, it's a table of numbers, and I put in this matrix, in this table, these things 0, 0, and the upper index here should be the row index. So this is just 0, 0, 0, and then 1, 2, 3, and then lambda 1, 0, lambda 3, 0, and this one will be lambda 3, 3. I just put them in there. And the eta without any index is this matrix. So that really is eta 0, 0, eta 0, 1, eta 0, 2, eta 0, 3, eta 1, 0, and so on. So I really have to tell you what I'm doing, where my indices go. I have a matrix which then doesn't have upper, lower, and whatever indices, but it's a table of this. And here I chose it to be this way, and here I chose it to be that way. you can do, well, we don't have other objects yet, we will in soon. And then the indices move around. You won't see, so this is where it gets confusing. This is now a definition, define this matrix. How does this equation look like using these matrices, just naive matrix multiplication? It's pretty boring, but we will get into trouble doing computations if we're not absolutely clear what we are doing. I don't know, it'll haunt us later. So matrix multiplication always comes over the adjacent one. So you have two matrices, this times this. So here it's I'm picking and it ends up there. The row index from the first, the column index from the second, and then the sum over the inner ones, so the columns here and the row here. And if I want to arrange for this, that the adjacent ones are multiplied. What's actually going on? I can move this in here, then the new and the new are adjacent. Well, but then they aren't. Then I have to transpose this. If I transpose this thing, then then this zero changes place and then it works. So I'm claiming that this upper equation is equal to this. If I define my matrices like there, then this matrix equation is that equation up there. Have I lost anybody yet? I might. You might think I'll worry about this later when I get an index. So the matrix multiplication wants to multiply two things where the indices are adjacent. Therefore, I turn this thing around and then this is in the middle. That's why it's in the middle. I can't just move them around. These objects, I can move wherever I want, right? They can go there, they can go there, yeah? Not on the other side, but I can move them here. These are just numbers that are multiplied together. These are now matrices. They have an order. So this sits in the middle. Right. You see something similar to the rotations? Ordinary rotation in the Euclidean space, R to the n, is a matrix that is O3 O equals 1. And here, this is like there's a matrix transpose times the matrix is 1. So these are almost ones. Eters are almost ones. Ether is just or negative ones. It looks like this. It's like an orthogonal matrix. But not really. It's an SO, well, it's an O. It really is an O 1,3 matrix. So this lambda is a matrix in the orthogonal matrix with this funny signature. And then it looks like this. And this would be an O. This is an O. This is the matrix. This is an O, whatever. D. Okay. Yes.
Why, if the eta is also a matrix, why are the indices both written not up and down, but both down?
Right. This is an absolutely good and fair question. And as I'm saying, this is confused. The matrix. Yeah, I haven't really introduced matrix indices. I have just written a table and put my components in there in this way. I just say put this number, this number, this number. This number happened to be taken from an object which has two indices. I'm now thinking, I've learned to think that these indices, these indices here are not the indices of the matrix. For example, I can do something, if here. I spelled it out. Nobody wants to ever spell this out. Even here, I stopped spelling out so much. Then soon you will go and write, oh, by lambda, I mean lambda mu mu. And there's where you get, there's where problem starts. Now you think, oh, these are my indices. And then you've heard the first index is the row index. So by looking, you know, oh, this is the first one really? Goes more to the left, it's probably the first one. But I don't know, if there's another matrix, okay, T, that's the T mu mu, are you reading row wise? Like when you read a book, you start from the top, is this the first? You don't know. So then you should actually write down what you mean. So here I would say mu nu, this is now the where you are in this business, the muth row will get the number that is here with this mu. If you want this transpose, you can either write this or that. So my point is, well, here I really need mu, and here I pick whatever I want. So if it's not clear, these indices I haven't introduced yet. This is the index of the matrix, and they are all of the same kind. It's just a naive multiplication that you learn in school or whenever it was. And we placed in this matrix these numbers taken from these, soon I'll call it tensor components. So therefore, it doesn't matter that they're all downstairs. I have these neutral indices of the matrices. They are all the same, of the same kind. There's no up-down business. And I want them in there because then this becomes that. And there isn't yet any other, there's no, I can't write eta with eta mu mu because it isn't even defined. There's nothing yet. So anyway, I have a collection of these things, and then I work with the matrices. Did this roughly answer your question?
Roughly.
Roughly.
I'm gonna ask later.
Which part am I missing?
I'm just confused. How do we know then for the top equation? How do we know then the rules for calculation? Because you said you have to transpose the left. How did?
Well, you have to remember what I defined here. This is what I mean by writing lambda. And this is what I mean by writing eta. If I start with this equation, I know how to translate it into matrix form, this. And if I was given the matrix form, I can translate it back by inserting these things. And lambda transpose is it's the transpose. It's how do I write this now? It's the name for this matrix where rows and columns are exchanged. I should really write it the long way. So now this is not this is the 1, 0, 2, 0. What used to go down is now going this way, and this is the lambda 0, 1.
Yeah.
It's just confusing, but it's not wrong or ambiguous. Fine, beautiful. So this can get in a box. You know, when the computations get a little bit longer than it maybe the matrix form, it's nice if you don't see any of these indices. You don't have to worry about naming indices with the same thing. So for example, here I was a little bit dangerous. I had mu, and I was tempted to call this other index the mu index, but mu was already sold to this thing. So, you know, with indices, it's sometimes you don't want to name them, and the matrix notation is more convenient. You don't have to name them. Anyway, so let's see some property of this matrix. And now since we're there, let's do this first. No, let's not do this first. So we set rho and sigma equals 0 in this equation. Then we have lambda mu 0, lambda mu 0, eta mu. And that is equal to, you said 1, didn't you? Equal to 1. Because it's eta 0, 0, and by metric definition, it's the 1. And the left-hand side is just the scalar product, basically, of the first column here. So with itself. And therefore it is lambda 0, 0 squared minus, now I'm writing some 1, 2, 3, lambda I 0 squared. The summation convention only holds for sum of all values, not 0. So I'm writing this. Why? Because this is now really positive or 0. It's a square, it's the sum of squares. So then I learned that lambda 0, 0 squared is larger, well, or equal to 1. This upper left component. Why do I care for the upper left component? Because it is the CT prime equals lambda 0, 0 times CT plus other stuff. So it's the factor in front of the translation of the t's. And that is, the square is larger than 1. So, okay, fine, it's larger than 1. That means time dilation, right? The moving clocks go slower. Can't go faster. On one direction, but I also like the sign because it goes to the negative, right? If it's less than -1, that would also simplify this one. So the lambda, that was the following. It implies either lambda 0, 0 is larger or equal to +1, or lambda 0, 0 is less than -1. And negative coefficient there means if my time goes one direction, like the t grows, and your t prime goes in the negative direction. That's the time reversal. That's weird. So we probably exclude these things. Don't choose your coordinate system with the flip one. Like you preserve the norm, thank you, but you will have a negative time. So don't do this. We call these the orthochronous or Lorentz transformations, and these are the bonus time Lorentz transformations. And these you can restrict yourself to them. Now, switching time, you can also switch space. Let's go and practice with this thing. If I take the determinant of both sides here, since the determinant of the product is the product of determinants, I get determinant of lambda transpose eta lambda equals determinant of eta. You compute the determinant of eta.
-1.
You're right. -1. Now I compute, I'll say this is equal to the determinant of lambda. That's the determinant of eta. I hesitated because I didn't like the -1. I wanted 1, but here's another thing. So determinant of lambda, but this is also -1, and therefore I can multiply by -1 if it works. And whether or not we transpose the measures or not doesn't make a difference. It's the same as in terms of lambda itself. So then we find among this that the square of the determinant of lambda is 1 rather than minus 1. And then we have the same two cases. We can have it either determinant plus 1 or minus 1. If it is plus 1, then we call the Lorentz transformation proper. And if it isn't, if it's minus 1, then we call it improper. So we have either the determinant of lambda equals plus 1, then it's a proper Lorentz transformation, or the determinant of lambda is minus 1, then it's an improper. And this is related to reflections. It's a bit complicated. The determinant is for the, say there's no reflection in space, the determinant is still negative or minus 1 if you have a non-orthogonal Lorentz transformation because of the minus sign or the negative value in the upper left corner. So if we have an orthogonal Lorentz transformation where the sign is plus, then negative determinant tells you that you have at least one reflection in one axis. You could have 3, not 2. And these form a set that we call SO1,3, the special orthogonal matrices of it in this Minkowski space. So this is, I don't care about the determinant. This is, I want it to be 1. I don't like any of the reflection business. I don't like the reverse the time, and I don't like the reflection because we want to talk about infinitesimal Lorentz transformation. So just a little bit. Someone had, like this snail, the snail transformation. The speed is really basically our speed, a little bit. And if I reflect the coordinate system, that doesn't work. Then your x 1000 becomes x minus 1000, and then it's not small, never. But it's just a jump towards the coordinate system. So we don't want that. So only orthogonal proper Lorentz transformations have infinitesimal versions. So this means the two observers have almost the same speed, right? Now we need to get a little bit faster here, I guess. Maybe not. Let's do a little bit more index gymnastics. This was a short physics internet, so we're giving these equations a meaning, time reversal and reflection. Now it's just absolutely poor boring math. We define various things. I guess we define first the scalar product. Before I only had the scalar product of the 4 vector with itself, with x with itself. Now I have 2 different ones. This is wiped down. So I have I have the vector a mu and b mu and then the a dot b, and I always write it with a dot. The scalar product is never AP. As with Twitter, I guess they write just next to each other. Oh, maybe I'm wrong, but there are books where they don't, like this. They will have it equally IKX all the time. This would be like one-dimensional thing, but now if you talk about the 4 vectors, and there will be a dot. So my scalar product will have a dot unless I forget, and then you have to yell at me. And it's defined the way it was for the norm, b mu theta mu nu. Now you say, I don't like writing the eta all the time, so you come up with the idea of lowering indices. And we define an A mu as this combination. That's bad. Let's see. It's more like this. So we define it as eta mu nu A mu. So this is what we define. Let's see how this makes this better. Doesn't make it much better, does it? I'm sorry. You see how this works? So if I can transpose one, I can change the indices because there's a diagonal anyway. So I can turn them around and put this in front. So then I have an eta mu mu A mu B mu. And this object is what I have here. Just relabeled mu and mu. So it isn't really obvious what I'm doing here. But for defining lower indices, this is the more natural placement of the indices. So I have something upstairs, multiplied by the metric, put this next to each other, and then have it downstairs. So this is now the definition of this object. And what is it? If this A is an A0 and then an A vector, and B, then this will turn the sign, no, will not, will keep the sign here and turn the sign there. Turns the sign of the spatial component because the magnetic was this. So the downstairs one is the same. If I write A with a vector, it is always the one with the upper indices. So A vector is always A1, A2, A3. Take the component of the 4 vector that corresponds to this object, and then we can keep the ones with upstairs. Not the one with downstairs because of the negative.
How do you write it if it's downstairs? Like you can't. But you just said like if you have a vector arrow, then it's upstairs. So
Exactly. So downstairs means they have
oh,
negative.
okay. It's yeah.
I have to do it explicitly. There's never downstairs. Like I don't have whatever. Nothing. It's just this is always there. And now this minus sign takes care of it. So now the scalar product is can be written as A mu B mu. Because when you multiply now this thing with the B, then it all works out with the sign. So now it's a little shorter. I could have also lowered it with B. So this object together is B downstairs. So this is A mu B mu. Wonderful. So you can trade them all the time, up and down. What more can you do with me? Now I've gotten them down. How am I gonna put them back up? How am I gonna raise how am I gonna raise the indices when I have them downstairs? You need to kind of invert this relation. So basically bring this to the other side, and the upstairs is that. But how do I get this to the other side? I have to have the inverse of this object, and so the inverse metric I will define as eta with indices up. It's a new matrix. Actually, it's the same matrix, but it's just a new definition, and it's called the inverse because it really is the inverse. If I multiply, so boring, isn't it? If I multiply eta upstairs with eta downstairs, I get 1. So eta mu with eta mu rho is really minus plus minus 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 plus minus minus minus, and that is plus 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 plus, and this is 1 or delta. And now with the delta, I write because there's one index up and there's one index down. Delta rho. And with this, I can raise the indices. Rolling, raising indices. Let's do it. Eta mu a mu. Anybody slightly unfamiliar with this? Am I boring you? Slightly unfamiliar, but just be honest because I'll feel better if I don't waste your time too much. So we have now various ways of writing the scalar product. Both indices up with conjective downstairs, the mixed representation, or we can now, because we have the inverse metric, we also can use A times B is A mu B mu eta mu nu. So there's four ways of writing the thing. And if you count this, it's the fifth. How? And not okay, now it's going to be slightly interesting. How does a lower index transform under Lorentz transformation? So if we have a mu is lambda mu a mu, so this is the prime. This is in one coordinate system, this is another coordinate system. So how does a mu transform? Now this is the question. Let's see. If I ask arbitrarily, are you slightly unfamiliar with blah blah blah? What is this? How does this transform? What is a mu prime in terms of a mu? What do I write there? Now we'll see if it's worth talking about it.
You go into a different coordinate system that moves with a constant velocity?
Yeah, that's my whole Lorentz transformation. So I have yeah. Usually write it like this. Damn. This is the one coordinate system, the x prime and the t prime, and this is the x and t, and I have a vector that sits in there. It's really hard to draw because it's metric. You would think you have Euclidean geometry, but you don't. So I have this this vector, and then I have also the two different ways, one with up and one with downstairs. Yeah. What do I do to these numbers? Yeah.
I'm not super sure, like I just, like I'm actually not familiar with this specific part, but I think you just squish the lambda between this, what did you call it? Between one of these, between two of these etas, and one of this is upper and one of is down.
Exactly.
I don't know which.
Exactly. There's and in fact, this is the only place where it's kind of interesting. The other one was really just up and down business. Here it's also something that is relevant because we want to construct invariants, and then we have to know how all these things transform with the Lorentzes and so on. So this you can we derive it from here. You have to lower this, and then we'll get this two etas. That's what you said. So you sandwich between the two etas, or it is also the inverse of this. So you can write two different things in there, and let's write the two. So A prime mu, the one we want to know, is eta mu nu A prime mu by Lorentz. Now by Lorentz transformation, this is eta mu nu lambda nu, haha, be careful, haha, so and then what else is there? Rho, a rho. But this a rho, let's do it in the same step. This a rho is eta rho sigma a sigma. Yes. So then this is the object that goes in there. Unfortunately, we have the mu. See, this is so annoying, but it's sandwiched between the two. Also, I'm not ever going to write all of this crap here. Three matrices. We'll define something. Look, this looks like I lower this index, and this looks like I raise this index. So all of this is going to be called lambda mu sigma. Now we have the new matrix. Remember this. Let's write this somewhere. By definition, we have now all of a sudden a new lambda matrix, which isn't the one we had before. Lambda mu is now there is eta mu rho lambda rho sigma eta sigma mu. So we can raise and lower down here, and then the objects with the lower index transform with this object. And that object is also the inverse. Oh, how do I see that now quickly? Well, the inverse. We know we have lambda mu rho lambda mu sigma eta mu y equals eta rho sigma.
Sorry.
Sure.
Can't we argue that the norm stays the same? So if the one transforms with the Lorentz transformation, the lower index one should transform with the inverse, so that
Maybe that's the faster way. Yes, I'm going to pick this up. Just telling you my way, but I'm going to switch to yours. Here I can see lambda times lambda is kind of identity. These were identities, so the one is the inverse, but it isn't really the lambda is the inverse of lambda, but with two etas. I can move them around, like bring the eta here, and then it is coming. So if I multiply this thing by an eta to touch this object, this is what I wanted. But that's the same as what you meant. Anyway, if I multiply this by eta, say your name, tau sigma tau, say, then here I have the eta mu, that's this, lambda mu sigma eta sigma tau is equal to the identity here, delta rho tau. And this is the lambda mu rho. So matrix and some other matrix is the identity. So these have to be the inverses of each other. So this thing is the inverse of that. So I can write that as lambda inverse. And then the indices are rho. What? Not rho, it's multiplying here. That sucks. This should be a sigma mu. How would you know it's that way? It is that way. Because it's multiplying. It has to have tau. It's that way. Yeah, it has to have an upper tau and it has to have a lower mu and it's multiple zeros. And this is, however, what we had there. Mu tau. This is also this is the by looking at this equation, we know that this object is the inverse of lambda, and by looking at this definition, we also know that this is lambda mu tau. So we know lambda inverse, or let's do the other, this one with the wrongly displacement, mu is really the inverse of the mixture and with this. That's another. Didn't fulfill my promise to pick up on the comment. Yeah.
How did we get to the equation below the one that's in?
To this?
No, the
To
one,
this.
yeah.
Oh, this is our famous is 013 condition, that the scalar product is the same. So we it was boxed a little earlier ago here. It's from this invariance of the scalar product. So the scalar product here transformed is equal to the scalar product without transformation. So that wasn't really derived. And this is the analog of the lambda, the component version of lambda eta. That
Oh, yeah,
what
yeah.
we have. Now let's see if time permits. No, it doesn't, to do it the other way. So the comment on the phone was a mu prime, where these indices have to be the same as a mu. So whatever this is transformed by, meaning the lambda mu, this has to be defined by some other measure. What measures name do I have? N for meter, mu, rho has to undo this. So these two things have to be the unit matrix, or this delta rho mu, and then in order to get that, so it shows you that this prime one transforms with the inverse of what this does. And the inverse we write here. And so if it wasn't confusing yet, now it is, because how would you write this? And that's one homework. I want you to start from the matrix with the normal placement, have really entries here, and then give me all the different things. What do you get? 2 down and this, and see which sign, and then you realize, oh, it's not so bad. It's just sign changes. But which signs? If you switch the first index, it's related to the row. So some rows will get minus signs, only the spatial rows, and this will be the columns. Names we will call not finished. We'll call the ones with the lower indices covariant components, and the other contravariant components. So A mu with lower indices. Let's start with the upper. The upper is lambda mu a mu. It's the contravariant transformation law or components. So the one with the upper are the contravariant components of the 4-vector A, and the transformation law that goes with upper is with this lambda, it's called the variant transformation, and then the lower mu is the one with the other thing, mu a mu, or if you like with the lambda inverse, then we replace it by the inverse. But since they have sort of the other way, I like to put it the other way around. So I can, because they are just numbers. Who wrote that? See, if you have the same version, then you have to go back and this is the covariance, so it has to be down, and then you have the new. See, it makes sense. Now you write them from the rest, from the right. This is the variant. I keep forgetting which is co and contra. It's just the opposite. I go to tiers. It doesn't really matter, it's just the opposite, so that when you contract an upper and a lower index, you don't get it. See, the whole point of this discussion is that we later, when we next time divide Lagrangians and all this, then we say, oh, we have something that doesn't change, the same for all observers. If all the upper indices are connected with lower indices, because if you have an object with upper indices, and then there's somewhere another object, could be a different guy, you have one local, you have another one who transforms, but this one transforms contravariantly, this transforms covariantly, and you know that they're the inverse of each other, and then it's good. So all we then have to do after having gone through this paint, we have to see that all upper indices are contracted with lower indices, and then my theory is Lorentz invariant. That's really the output of all of this. What we next time need to do is that a bit more interesting because we'll have derivatives. So stuff changes, not just vectors. We have derivatives. Then we have derivatives which have to act on something. We have fields, and then we can put indices on the fields. So we can have the ones without any indices. Then we can have spinor indices. What's a spinor? Then we can have vector indices, fields with vector indices, and they all transform. And we have to construct invariants out of all of this, maybe even with derivatives on them. And so to figure out how all of these things transform in a Lorentz relation. So this is the warm-up. I know it was kind of dry with this in this stuff, but it'll get more exciting. It was also supposed to be yesterday, so the exciting part today. I have a minute to just write you another dry equation, which I don't write because it is dry, but here it was the contraction of the upper ones. You can also get one when you contract the lower ones with the inverse metric. Then guess what this is? I have contracted the lower ones.
Either with the
It's the eta and then whatever I have here. It's very different from this. And you should from this. And you should derive it, and what you'll have to use is this. Yes, we can. Okay, this is a little bit about light cone, but why would we? Question, comments? That was familiar, right? More or less. Good, but don't forget it until Thursday.